Welcome to this NPTEL lecture on principles and techniques of modern radar systems. We were discussing SAR systems, synthetic aperture. Now, we have found the cross range resolution and we have seen the Doppler shift of the signal due to the SAR motion. Remember that Doppler frequency of each signal is almost linearly varying near t is equal to 0. Near t is equal to 0, that quadratic variation becomes almost linear. So, the radar echo signal is not a constant frequency signal. The Doppler filter in the receiver that will have to differentiate these two linearly varying frequencies close together, but with present days electronics that is not a tough problem with digital filters. In case of constant frequency signal, we will see that SAR's phase compensation is a linear function of time. In SAR filter, this phase compensation is a quadratic function, that we have already seen that phase is quadratic. Different Doppler filters are required for different ranges, and if R 0 is maximum, the slope of the f d versus t curve is less. Okay. Now, let us see that what is the limit to this cross range resolution. It is seen that the cross range resolution is inversely related to L. So, obviously, increasing L improves the resolution, but there are two limiting factors of L. So, let me write that two factors limiting L. The first one is increase in processor size. Why? Please see what is L. This L is, so during L many pulses are being sent and they need to be kept, all of them. So, that means the processor will have to have access to a good storage. So, if I increase L, the storage will increase and then it will have to compensate, phase compensate each of those echoes. So, computation will increase. Also so we will need to say that because these are generally satellite systems etcetera or aircraft systems. So, on board you will have to have that. So, increase in processor size means memory and processing time increases. So, I can say this is increasing, this is also increasing. You remember processing time increase means to generate an image you will take longer time etcetera. But that I will say that not the main thing. Second thing is a geometric limitation, that point P should be within real antenna beam. all through the observation section L. Now, this point we will discuss now. Actually, you see that this is my, let us say, L by 2, this is plus L by 2. The point 1, 2, 3, 1, 2, 3. So, the point P is here. Okay. This is my center point A. This is my R naught, and this is our y axis. So, at this point, when the radar is at minus L by 2, I should have the beam at least like this. That means, beam is the upper portion of the beam is, so this is the beam, the upper portion of the beam is illuminating point P, and let me call the horizontal, because this is at the ground. So, horizontal beam width, let us call it phi h, and that the upper portion of the beam should touch P. Similarly, from here I can say that lower portion of the beam should touch this. So, these are the two extreme points. So, let me call with this, what is my phi h? This is the horizontal beam width of the SAR antenna. Here I will have to make one realistic assumption that R naught, which is the range, you see these are all aircraft based system or satellite based system. So, R naught is much greater than L. So, we can say not theta, we have used different things. So, phi h in radian, this will be, so from this geometry easily I can say L by R naught. This, if R naught is much greater than L, then this is L by R naught. Also we know for an antenna the beam width is given by lambda by d, where d is the real aperture length. I am saying we generally call it dimension, the largest dimension of the antenna. So, in this case real aperture length. So, I can say that L by R naught is equal to lambda by d So, L is equal to lambda r naught by d. Now, this is the maximum that we can have. Maximum L should be like this. If L is more than this, then this point P cannot be illuminated by this. So, basically I can say that this is the condition for L max. The maximum L can be this. So, the second factor of this point P should be within real antenna beam, also the observation section L tells me that physically you cannot have a SAR antenna length greater than that value. So, if I put that into this equation 11, I get the minimum possible resolution value. So, I can say from 11 equation 11 I get delta y mean, because this is maximum and this is inversely related. So, delta y mean will be lambda r naught by 2 L max, and if I do that, naught by 2 into lambda r naught by d, it becomes a surprise that it is d by 2. I think we should give it a number, but before that I will say that this also generally is an important thing, because from this approximation this came, and with that this will become 13 or this, that the cross range resolution, the best you can have is half of the length of the antenna. So, if you have a 1 meter dish, you cannot have a cross range resolution better than 50 centimeter, like that. So, this is actually you see the I will say the you cannot have everything. So, you cannot go on reducing L, and whatever the real, actually we synthesized the antenna, we wanted a larger antenna, but resolution we cannot beat that. So, resolution will be half of the size of the antenna, but still that is a very good value and people are using it, etc. Now, here one question can be asked that okay, I will make my antenna, the real antenna smaller, that will improve my resolution. Can we do that? I think no SAR engineer will recommend that. Why? Because if you make your antenna smaller, actually the gain of the antenna that will fall. So, you will have to have large amount of power to for the same thing, I think. So, receive signal strength will decrease if the gain is less, because it is a two-way gain for radar, because it is sending and again receiving. So, both the gains will decrease. So, that will make your transmitter more powerful, you need to make, etc. So, actually there is a cross check conflict between these, that what will be the optimum size of the antenna. To answer that question, actually we need to find this resolution and what is the power of the transmitter, that we need to have an expression that we will derive. But I am saying actually you see this conflict, that if you want to reduce the size of the antenna, the power requirement gets more. The same this conflict was there in downrange also, that pulse, when we discussed pulse compression, actually we saw that if you want to have better range resolution, you should have short pulse, but short pulse will not be able to carry power. So, that is why pulse compression was invented, that you have long pulse, you carry power, but at the processing time you get the benefit of the small pulse. Similarly, here in the SAR, that you synthesize the antenna etc., but up to a limit, that limit is this d by 2. Now, let us come to the point that power versus resolution expression. So, here again we will start that L we are taking as L max, and we cross range resolution, I am again writing for a reason, we have already found that expression delta y, where is delta y, delta y lambda r naught by 2L, but you see this is here it is r naught is at t is equal to 0 you get this resolution, but at other points it is not r naught, it is r. So, that is why I rewrite that delta y is lambda r by 2L, and also here I say that for ground, actually people have found out the something called emissivity, which is related to the RCS of the ground by this thing, that if you suppose you have this ground and let us say that this is your y direction, this is your x direction. So, these are your x direction. So, let us say that my resolution in x direction is delta x and here it is delta y, then delta x delta y into the emissivity as a function of alpha, this is angle of depression. That means, the way the radar is looking at the ground, the radar is flying like this and point P is here. So, it is looking at the angle of depression. So, something like squint angle. So, this term is called, this is this sigma naught, this is called emissivity. People have found for various for the various regions the emissivity values are known. So, we will use that because radar people use it a thing. So, that means, for an unit area what is the emissivity, that this is the relation between. So, I will say this is RCS and this is emissivity. So, let me call this is an important relation. So, this is, let me call equation 15, and we have already found earlier in the basic classes the SNR expression for radar. So, if we have n number of pulses integrated, the SNR improves by n. So, that is why I am writing like this, P t g square lambda square sigma by 4 pi whole cube r to the power 4 k T b. Here all terms have their usual significance. T is the effective temperature of the receiver, B is the receiver bandwidth, and here for the bandwidth again B we can relate to the pulse width, and we have in the resolution classes seen that it is not exactly B is equal to 1 by pulse width, it will be some factor. So, that I can write I think given. So, let us say some P is a constant, it may be 2/3, it may be something. So, T p is the pulse width. Now, what is the value of this n, that for SAR we can find out, because SAR is moving, the radar is moving with a constant velocity and it has a PRF. So, immediately we can find what is the value of n. So, n will be, the PRF is FR and time L by V is the time. So, in observation time T, how much if the FR is the PRF. So, FR into T will be the number of pulses. So, this we can put FR, and L again is L max. So, that value we can put lambda r by 2 V delta y. Actually, by this we have brought this delta y, the cross range resolution. So, using equation 11, we have said this L is equal to L is L max and delta y will be again d by 2. So, doing all this you will get that n will be FR lambda by V r by d. So, I think this will give a number 17, this will give a number 18, and also the time average power of the transmitter, that we have already found out Pt into Fr into tau p. So, this we will call 19, and also for an antenna we can say that for a generally horn type of antenna, it is a aperture antenna, we can say 4 pi by phi h phi v in radians into the aperture efficiency, antenna efficiency. This is antenna efficiency, these are the bandwidths in the horizontal and near plane. This is coming directly from antenna knowledge. So, putting this value of phi h, we can write G will become 4 pi d by lambda phi v rho a, that will make it equation 21. And so, putting all this P average, this can be written as, if I put all these things, it can be written as 2 pi k T e beta phi v square by lambda emissivity rho a square into r cube v by delta x delta y square into SNR. This we can call equation 22. So, we can say that it is, these whole things are constant. You see, all these things are constants into r cube is also we can assume, because this is the range for a fixed range, because we are seeing power versus resolution. So, r cube v will also go. Finally, we are left with delta x delta y, or I will make them together, delta x delta y into delta y into SNR. Now, delta x delta y I can call target area. So, this is the target area. So, what we are seeing is the power, smaller the target, more transmitted power required to obtain necessary SNR. Actually, this additional inverse dependence of delta y is coming from SAR cross range processing. So, if delta y is decreased further, more PT is required to keep a fixed SNR, or conversely we can say SNR will degrade if PT is kept fixed. So, you see that this is the problem, that you cannot go on decreasing delta y further and further, because then your PT requirement will be more, and all transmitters has a limitation on final how much PT it can give. So, the real antenna aperture cannot be decreased beyond a point found by PT. So, cross range resolution even after SAR processing is dependent on radar receiver detectable SNR. Also, it suggests that one cannot go on reducing antenna size to improve cross range resolution. Please mind it. So, you will have to now within this, as an engineer's choice, you will have to make a value that what will be your resolution. So, do not expect that cross range resolution will be as fine as millimeter, etc. For ground mapping or earth mapping, that is also not required, but nowadays it is getting required for earthquake prediction, etc. SAR, ISRO and NASA, they are having a joint project that they are trying to predict whether any earthquake is possible in any place on earth. So, for that millimeter type of resolution, etc. may be required, and that SAR system is being developed also. So, for that they are also using some other means, the polarization diversity, etc., interferometry, that those concepts they are using. But it is good that actually what we are saying, that it is you cannot go beyond that, but now those limits are getting challenged, and people are trying to find out cross range resolution of the order of millimeter also. Hopefully, one day someone will teach that in a SAR processing you are having with a real antenna also you can have so less power, that small antenna, small power, but with processing you will get all the imagery possible. Okay. So, with this I conclude this SAR. One thing is remaining, that what is the structure of a SAR processor, the architecture of a SAR processor, that I will do in the next class. So, what we have seen, that how from the basic movement of the SAR you can find out the phase history, you can find out the cross range resolution expression, then what is the limit on that resolution. So, that turns out to be half of the real aperture length. Now, the question is, can we use small antennas? The question is, ultimately you are governed by the power handling capability of the transmitter. So, if you have infinite power, definitely you can go on reducing the antenna, but with a limited power handling capable and transmitters, you cannot go on reducing D. So, you fix from an engineer's perspective in the application at hand, you fix a particular antenna diameter, and then you diameter or antenna length, maximum dimension of the antenna, and then your cross range resolution cannot be better than half of that. So, with that some basic SAR thing, we have seen how what is the resolution concept in cross range. In the next class, the SAR processor will do, there also will use the same, that phase history part, that at various points, that means if in the movement of the SAR at various points I transmit a pulse and get the echo, I know what is the phase of that in terms of a reference, and then we will see how the SAR processor does that phase compensation and focuses the image to a particular point. That is will be the topic SAR processor in the next class. Thank you.